Okay, let's continue maybe. And sorry, we're having some minor technical difficulties here with our microphone for the recordings for the video lecture. So, well, I don't know whether we'll sort that out easily, but we'll sort it out somehow for the lecture that was just given by Henka. Yeah, I guess if you did take the chance to go to the Matplotlib plotting gallery, I just went there and copied one of these examples showing different interpolation methods. And most of them, as long as they don't require some image file or something like that to be present on your computer, most of them you should just copy and paste. So I literally just copied this from the Matplotlib page and then ran it, and it produces a plot that looks like this. So kind of interesting to see all the different options there are for how to interpolate between points on images. So again, we would encourage you to go and play around a little bit there, because that's the easiest place to get started when you want to do your own plot, especially if you don't have a working example to start from. Usually you can get a pretty good jump start from the Matplotlib plot gallery, or just going on Google and looking around. For us, now we're going to turn to slightly more advanced plotting with Matplotlib, and our goal here is that by the end of this little section of the lesson, we'll produce a plot that looks like the one that's shown here. And what we have here in this case is something we'll see about halfway through the lesson called subplots. So this is one figure window in which there are 4 different plots displayed. They're called subplots in the name that's used in Matplotlib. And in this case, we have seasonal temperatures for winter, spring, summer, and fall for the year 2013 from the Helsinki Malmi Airport observation station. So we'll make this plot at the end. As before, we're going to be working with temperature data. In this case, as just mentioned, this is data from the Helsinki Malmi Airport for 2 years, 2012 and 2013. And these are hourly temperature measurements, or actually more frequently than hourly. I think it's actually 3 times an hour that they have a value recorded here. And the data file is a bit bigger than what we've looked at previously. So there's about 16.5 thousand lines in this data file. And we're going to work our way through that data as we explore some additional plotting. So unfortunately for this, sorry, I have to log myself back into this computer. Unfortunately for this lesson, to do some of the analysis, we're going to use a few things from NumPy that might not be familiar for those of you who were in the pandas lessons. I apologize for that, but there's not too much that we can do to avoid it. Hopefully you at least get a good sense of how things work here, and if there's some stuff we do that's NumPy specific, just bear with me and type it in and hit enter. You don't necessarily need to understand everything. So we're going to start here in our advanced plotting lesson by just importing Matplotlib like we did before. We're using another Jupyter Lab or another Jupyter notebook, so we need to import matplotlib.pyplot as PLT. So that'll make it easier for us to use the plotting commands out of the pyplot submodule. And then, like before, at the top of the file here, we can load our data. You don't need to worry about how we're doing this right now. You're welcome to go back and look at it. But if you prefer to load it using the NumPy way, you can basically just Shift-Enter on these first 4 cells. We're only going to pull out the date and temperature variables from this data file to work with those. So you can basically just kind of shift enter your way through these first 4 cells here. If you want to do it using the pandas way, again, as before, we'll end up with exactly the same values in our arrays that we're going to plot. But you can just run the cells under pandas if you feel like that's your preferred way to work. You've got examples of how to load this kind of data here, and we're not going to spend time talking about how we've loaded it, but just more that if you want to refer back to the start of the lesson, you can see what we did to get the data loaded in. And if there are problems, just let us know. So the first thing we should do is we've got a lot of lines of data here, and certainly we don't want to go through one by one and look for things like missing data values. But if we have missing data values, those are typically going to show up as a not a number, NaN, value in both Python or both NumPy or pandas. In this print statement here, you can just run this cell as well. I've tried to kind of shortcut things and make you not have to type in too much stuff. But if you print out the number of dates, you see that we have 0 NaNs for the date column. Not a big surprise. But we have 26 missing values for temperature. So we're going to have to clean the data up a little bit. To go back to what this cell did, okay, you know the print statement by now. Here we're using a function in NumPy called isNaN. So this basically will just return a value of true for all of the values in a NumPy array that are listed as NaN. So in this case, we do isNaN for the NumPy array called date. And then we take the results of this and then do a dot sum. So this is kind of shorthand notation. We could do this in a few different lines if we wanted to, but it's all done in one quick line here. So we just find out how many values are NaN in date and just add those all together. Do the same thing for temperature and add them all together, and that's what's printed out here. So anyway, we know we've got some cleaning up to do, and that's going to be our first little task we have to handle here. Now, there are easier ways to do this in pandas if you want. Again, since we're kind of working with this stuff in a format that we try to make it so that everyone can follow along, whether you've done pandas or NumPy, we're going to clean this up the way that I've shown the students to do in the group that's learned NumPy, and that is to use these things called masks. So a mask is essentially like a true or false array that allows you to easily remove values from your list of values. So we could do something like create a variable called temp mask, and it's going to be an array that's the same length as one of the columns in our data file. And I'm going to type this in with one little thing missing here just to explain it first, and then I'll go back and fix something. But we'll use our np.isNaN, as we did before, of temp. So we remember that in temperature we had these 26 missing values. If I ran this as it's typed in here, this is going to give me only the not a number values as the mask value. So this is going to be true for any value in temp that is a NaN value. What we actually want is to create a mask that is true for everywhere where we have data, not everywhere where we have missing data. So just the opposite of what this would produce. And we can do that using this tilde character. For those who've sat in the NumPy lesson, you've probably already had to work your way through trying to find that character. On the Finnish keyboard, at least, it's going to be something like, I guess, Alt, and then the character that's just to the left of the Enter key that has like the little hat and the 2 dots on it sideways. I don't know, at least on the keyboard that's down here, there is a little tilde character there. So you have to press Alt and then that key to get the tilde to appear. It's easier on some other keyboards. But essentially, this is going to give us all true for the values in temperature where we have an actual number. And it will be false then for all the values where we have missing data. The nice thing about that is that we can then take our list of temperatures called temp and say, well, we only really want temperature values for the cases where temp mask is true. If you've done the NumPy stuff, maybe this is sounding a little bit familiar. If you haven't, don't worry about it. All we're doing is just cleaning out values the same way that we could do in pandas with the drop NA function. This is just how you do it in NumPy. Since we've converted our pandas data frame into basically an array in NumPy, this is kind of how we have to do it with the data at this point. But you can take my word for it. This is going to get rid of our NaN values that we had in temp. In fact, if you want to demonstrate that, you can go back up to the cell above where we printed out the number of NaNs, and you should see when you run that there are now none. And we've basically just removed 26 temperatures. Now, we're not working in a pandas data frame here. We're working in just these column arrays. So if we remove 26 temperatures from our list of temperatures, we need to also go and remove the dates that correspond to those 26 temperatures we just removed. That's part of the reason why we make this mask as a separate thing here, because we want to now clean out, if we drop these 26 temperatures, we want to drop 26 dates that correspond, and we can do that simply by doing date equals date for temp mask. So again, since temp mask will give us only the values where we have an actual temperature, this will drop out the values where we had NaN for the temperature. Otherwise, our two different arrays are going to be different lengths. One would be 26 values longer, and if you go to plot those things, you're going to have problems. So now every single one of the dates should have a corresponding temperature.
This is actually exactly the same process that with pandas we are doing with using the .lock, but actually we are separating these things in different processes, and we need to do array at a time, whereas in pandas we just do it once and it basically deals the whole data frame.
Yeah. So you can do similar things in NumPy, but it's a little bit more complicated. So this is the way that I think is sort of easiest to understand, if you can believe that. Okay, so now we have our temperatures. You may remember that oftentimes when we get these data from various places like the U.S. National Oceanographic and Atmospheric Association, the data for temperature are often in Fahrenheit. So we can convert now our temperatures to Celsius, and we can do that pretty easily by just saying temp Celsius equals temp minus 32 divided by 1.8. We could make a function to do this. We could do this a handful of other ways. We could loop over and do every single value, but with NumPy arrays, one of the nice things is that you could just do the math with the array here, and it will create a new array that's the same size as what you put in. So if you run that now, we'll have something called temp Celsius. If you want to add a cell here, you could print out, for instance, temp underscore Celsius, and we'll just take a slice of values from 0 to 10. So the first 10 values out of this array. Again, I don't know if this is something you've done in a similar way in pandas, but the array slicing is something that should be familiar, at least from dealing with lists earlier on in the course. And well, these are temperatures for January from this location. It's in the northern hemisphere, and these look like pretty reasonable temperatures for January somewhere in the northern hemisphere. So good, now we have temperatures in Celsius, and we can move on to the next topic, and that is using these subplots. Now, what we want to do, if you remember from the start of the lesson, is we want to make a plot for winter, spring, summer, and fall, so the 4 different seasons, and each one of those seasons then we need to pull out some data that corresponds to that season. We're going to do this for the winter of 2012 to 2013, and then the spring, summer, and fall for 2013. There are lots of different ways in which we could chop up this data, and you've already seen some from the exercise last week. To make this as fast as possible, I'm just going to simply use the number ranges for the variable date. And I'll show you how this works for the winter, and then spring, summer, and fall are already entered for us down below, so we don't need to worry about that. But we're going to start again by making one of these masks. So we're going to make one called winter mask. And winter mask is going to be dates that start. So we want to say the date has to be greater than or equal to the first day of winter. And for us, the first day of winter is going to be December 1st of 2012. So that means 2012, 1st of December, so it's going to be 2012, 12/01. That would give us the format that we have our dates in, which is 4 characters for the year, 2 for the month, 2 for the day. And then actually we have 2 for the hour of the day and 2 for the minute, because we have these observations that are more than hourly. But we can just put that in as 0000. So the first hour of the first day, or first hour and first minute of that day. So the date that we're interested in should be at least starting from that. And for our season of winter, we're going to say that it goes all the way until the date is less than the first day of March. So we're doing December, January, February as our winter. So the first day of March we don't want to include. And that's for the year 2013, so 2013. March is the 3rd month, first day, and then 0000 for the hour and minute values. A little bit clunky to type this in, which is why I didn't make you do it more than once. But this is going to just give us a range of dates that correspond to the winter then that meet these 2 conditions. Has to be at least the 1st of December and can be no later than the first day of March. And frankly, actually, that's excluding the first day of March with the way this is set up. Okay so far? Yeah. So once we have our mask, we can then select our winter dates. We'll just make a new variable called winter_dates. And that's going to be equal to the values of date that are within our winter mask. So we just defined this true or false array, this mask, for anything that meets our dates of being at least the 1st of December, but not any later than 1st of March of the following year. And now we just extract those dates from this list and store that as winter dates. And we can do exactly the same thing for the temperatures. So we can make a variable called winter temps. And winter temps will then just be temp Celsius, because we want to be working with our Celsius temperatures here, for winter mask. Again, if this is not totally clear to you, don't worry too much. All we're doing is just extracting a slice of dates to correspond to a given season, and there's several different ways that that could be done, perhaps more easily even in pandas, for example.
This is actually really good kind of example now for the pandas. I'm not sure if you actually know this, but what we are doing here is exactly the same that we do in pandas. So inside the log function, if we want to do selection based on 2 different variables, as you see the winter masking there, so basically how we do selection based on 2 different criteria, this is what we are actually specifying inside there. So we specify, for, in our case, the date that we use here, which is an array, NumPy array. What we will specify in pandas is that we will basically use the data frame and the column as there. But we are in principle doing exactly the same things. And I assume that what is actually happening under the hood is exactly this.
Yeah. It's just that it's usually easier to do in pandas.
Yeah.
So, okay. So anyway, if you've typed all this in and everything is good in the world, when you run this cell, you should get no errors. And all we've now done is we've extracted out our dates and temperatures for the 4 seasons. That's good. That's step 1 to being able to plot the data, as we have to slice it up. We can now take a look at how the different seasons look individually. And we can do that just by doing a plt.plot. We've seen this before. And here's what I mentioned earlier about not needing to list a second variable. We can just do plt.plot for winter temps. And if you run that, you should see something that looks a bit like this. In fact, if you want, you can run the 3 cells beneath that and you'll see the temperatures for the spring, summer, and fall as well. Get a nice example of the temperature warming up in the spring. Pretty steady temperatures in the summer and cooling down in the fall. We're not so much to that stage right now this year, but I guess it's coming. So anyway, we have our 4 ranges of temperatures, and now we have 4 separate plots, and the next task is to put those into a single figure. Are there any problems with anything so far? Okay. So maybe we can give some help to anybody who's stuck. Okay, yeah, so we've got now our 4 different plots. One thing that's going to be useful for us, or that's kind of a good idea in general, is like if we want to look at these 4 different seasons and kind of compare them, I'm pretty much of the mindset that we should have the same range for temperatures on the vertical axis for the different seasons in order to be able to see the differences. Like if we put these 4 plots together, we could see, for instance, now that the maximum temperature in the winter is maybe a little bit more than 5 degrees, but it goes down to maybe minus 25. And in the summer, the maximum temperature is close to 30, and the minimum is more than plus 5. In order to make our subplots all have the same range of temperatures, we can define the bounds for the minimum and maximum value we want to have on the the y-axis, the vertical axis of the plot. And that's fairly straightforward to do. We're just going to define a variable called min temp. So this is just for the purposes of plotting. And min temp is going to be temp underscore Celsius dot min. Built-in little function in NumPy, I guess we should call that a method, properly speaking, but it will calculate the minimum temperature in a NumPy array, in this case temp Celsius. So that's good. We can do the same with max temp. I guess if you've probably already figured out how this is going. We'll do temp underscore Celsius dot max. So this will give us the minimum and maximum temperature values in our data that we have here. I'll show you something maybe, actually I think we're okay in this case working with temp Celsius. If we tried to run this with our NaN values still present, we would get back NaN for the minimum and maximum temperature, which is another reason why we want to make sure to clean the data. But if you run this, you should see that we actually have the rather remarkable scenario here that the maximum and minimum temperature are in fact equal to one another with opposite signs. So minimum is minus 28.8 and max is it's positive 28.8. Just a bit of a coincidence in this case, and as far as I can tell, that's not a mistake. So if we go and clean the data up a little bit more, average the hourly temperatures into daily or whatever values, this kind of variation goes away and things look a little bit more reasonable. But yeah, so now we have this max and min. There's one thing I'm missing here, and that is the min temp. When we go to plot it, we want to have a little bit of padding so that when we define the range of temperatures, we don't set it to be exactly the minimum temperature so that the line hits the bottom of the plot window, but that we give a little bit of extra space. So we could take that min temperature and maybe subtract 5 degrees. You could do less if you want. You could do 2 degrees. Depends on how much padding you want. In fact, you know what? Let's do 2 degrees. And we'll do the same for the max temp. We'll just add 2 degrees. So this will give us just a little bit of extra space on the range for the vertical axis on the plot so that our line doesn't hit the edge of the window and that we don't have tons of white space that's just unused on the plot. So you can run that again. If you run that cell again, you'll now see that your minimum and maximum temperature should change. And now we can move to making our first set of subplots. Things will look somewhat similar, yet a bit different here when we do the subplots. So we'll kind of go step by step, and I think we're doing okay on time, so we should be good to do that. One of the big differences here when we make the subplots is we want to be able to refer back to a specific location on the figure window. So one of the plots we want to be able to refer to in order to say which data should be plotted there. In order to do that, we need to assign some things, some variables related to the plotting, and we'll do that like this. We're going to make one called fig and another called axes. So these are two variables that will allow us to refer to things that we're going to be plotting. And we're going to set them equal to plt.subplots. Subplots is the intuitively named command for making subplots. In this case, we're going to do n rows equals 2. So 2 rows of plots, and n calls, number of columns, equals 2. So we'll have a 2 by 2 grid of plots. We're also going to go ahead and set the figure size here because we can. And we'll set it to be 12,8. So 12 inches wide, 8 inches high, because that's what we're going to use, and Matplotlib uses inches for some reason. So we can define that, and what this is going to do is basically give us a variable called fig and a variable called axes with which we can refer back to specific plot windows or subplots on the figure and modify things as we like. Just to make this a little bit more clear, if you type in axes as the second line here, and when we run the cell, what you're going to see is some output. So I'll run this now. There's two things that are output. One is the kind of basic empty subplot window. Everything looks good so far. We have 2 columns, 2 rows of plots. We haven't given any data to plot yet, so they're empty, and that's not really a big surprise. But what I want to draw your attention to is up here, where this output that looks kind of weird about this axes subplot object. The main thing in here is that this is the output when you run the axes command. And what it means is that we actually have here 2 lists that are nested within each other. And there's a little bit of text underneath here that explains what this means. But essentially we have one pair of axes that are referring to the values on the first row, and then the second pair of axes that would be referring to the values or the plots on row number 2. There's lots of different ways in which you can name these things in the hope that you can understand which one is which when you go to start modifying the plots. And we'll go ahead and just make our lives a bit easier by changing the way in which we can refer to specific plots down here. It might take a moment to kind of read through the lesson materials to kind of get the sense of what's going on here. But if we want to talk about things that are on the first row, we could say that AX11, so the first row first column. That's what we'll call this variable ax11. And that's going to be axes, and since we're doing NumPy or Python indexing, axes 0, 0. This is just our name. You could call this whatever you want, you know, axis 1, 1 or ax 1, 1 or whatever. There's lots of different ways in which people do this. I'm going to copy, well, actually, I'll just type it in. We could say first row, second column, ax12 is then equal to axes. And now we're going to go 0, 1. So the first index in this case is referring to the row number, and the second index is referring to the column number in this set of plots we have here. So ax11 would be the top left, ax12 would then be the top right in this case. And if we add in then ax21, so second row, first column, that's going to be axes 1, 0, and then ax22 would simply be axes 1, 1. It's a little bit clunky, but I don't think there's a much better solution for this problem. There are other ways to do it, but this is a kind of nice way that will allow us to go back, and if we want to modify something about one of the plots in particular, we now have a way to reference each one of the plots individually. So, yeah, if I'm going too fast at some point, just don't hesitate to say something, but I don't hear a lot of keystrokes, so I'm kind of assuming that you guys are caught up at this stage. Okay, so we've got this empty plot window or empty figure with these 4 subplots, and now we're going to add some things on here. We'll do a couple things that are new with the plot command in general, and one of them is we can set the line width, so how wide the line is that we're going to plot on the figure. And we can do that just by defining a variable called line width. You could actually call it anything you want, but line width is a nice name because it refers to the width of the line. And we'll set it equal to 1.5. This, depending on the size of the figure you make, you want to play around with these line widths, but 1.5 looked pretty good when I did the lesson material, so that's what we're going to go with. And before, we had used this plt.plot command to make a plot. Well, that's what we're going to do next, except now, if you use plt.plot, it will just plot on the most recent one of the subplots that was defined. So it's going to automatically go to the column 2 of the second row and start making your plot things there. If you want to refer to a specific one of the subplots, you need to then say ax11, for instance, to say I want to plot something in the top left subplot. What do I want to plot? Well, in this case, I want to plot winter temps, because we're going to put the winter temperatures on the top left, just like we saw in the example at the top of the lesson. We can also change a little bit the way in which we format the plot here by using the C parameter. You can also, I think, say color in its place. And with C, you can list the name of a color here. And again, if you look on the Matplotlib PyPlot documentation, you can see what are the acceptable color names you can type in here. We'll do blue, just because that's a pretty typical color to use for the first plot in Matplotlib. And we're going to set our LW, which is the line width parameter. Again, I think there is a longer name you can give it, but we'll set that equal to the value of line width, the variable we just defined in the line above here. So here's the data we're going to plot. C is going to allow us to change the color. We could also use that format we had used before. For instance, if we want to use blue, we could just put a B in quotation marks without saying C equals blue. But if you want to use a color like orange, green, or brown, I don't believe there are shorthand color names for those in Matplotlib, so we have to give it a color name here. And then we just say the line width. So we've got that set to plot our data for winter, spring, summer, and fall. The last thing we need to do now is you remember we wanted to make sure that all the plots had the same range for the y-axis. So we're going to set ax11.setYlim. This is the function that you can use to set the range for the y-axis. Of course, there's one you can do for the xlim if you want to as well. And we're just going to go with value of min_temp for the minimum value and max_temp for the max. The way that this function works is the first number you give should be the lowest value and the second number should be the upper bound for the limit of the axis range. At this point, the only thing we haven't seen to this stage is just this additional thing down here called fig. You could put this into a Jupyter notebook whenever you want the figure to appear, especially like here, we've already created our figure window earlier. If I ran this command without fig there, I won't get any output, so I have to tell it like display the figure again. But if you run this, you should get some colorful lines in this 2x2 subplot shape that we have defined earlier. If you have problems with that, let one of us know and we can see what went wrong. But essentially, the key things here are that we've got winter temperatures, top left, spring to the right, summer, and then fall in the second row. And you can see that the range of temperatures on all four of the plots for the vertical axis is the same. We don't have labels for anything on here yet, so it's kind of like you got to trust that that's what we're plotting, but that all looks okay so far. Now this brings us to one other thing we have not dealt with very nicely yet, and that is if you look at the values on the horizontal axis, does anybody have any idea what these values are? Yeah, so it's not the date, it's actually the index value, because when you just give one variable in plt.plot command in Matplotlib, it assumes the index value for the horizontal axis. So yeah, it goes from 0 to something more than 2,000. That's the number of hourly or sub-hourly measurements that are taken in this 3-month time range. It'd be much nicer if we had actual date values on there. And so that's what we're going to do, and I will tell you that it turns out plotting dates on the horizontal axis of a plot in many different programming languages is more difficult than you might expect. As you know, dates are not sort of like continually increasing, but you go for like the number of days in a month, and then you jump back to 1, and then you go to the number of days in the next month, and you jump back to 1. And then when you go, for instance, for years, you jump by a large amount. So if we have something that's represented like as a number for our date, where it starts with the year, 2012, and then the month, and then the day, if you plot that as just a numerical value on your plot, you get these big jumps between each one of the years, and it just looks like garbage. So we're going to treat the dates properly, but to do that, we've got to meet somebody new, and that somebody is the date time module in Python. So I hope that you're all able to do the following, and that is from datetime, import datetime. Boy, I hope this works because I did not test this on the CSC notebooks or on Binder. It works for me. I think it's a built-in module in Python, so I hope that everybody's able to do that. Lotta, if you're free, there's one question here. So all this is going to do is just import a set of functions called datetime from a module called datetime. And that's going to allow us to convert our numbers that we have for the dates into something that is understood by Python to actually be a meaningful date. The first thing we have to do in order to convert those numbers to dates, though, is we have to convert the number we have listed in the variable date, or for each one of the seasons, the winter dates, to a character string. So instead of being an integer, which it is right now, we need to convert it to a character string. And in this case, we could make a variable called winter str. So the winter character string is simply winter dates dot as type str. So for those who've done the NumPy lesson, you've seen this as type thing before. For those in Pandas, I guess maybe you haven't seen this, or have you? Yeah, you have. Okay, very good. So type conversion, right? No big deal. We're just going to convert from integer to a character string. And we could go the route you've done before, like chopping up that character string into separate year, month, and day. We're going to do it a little bit differently here because it's easier to plot if we convert it to this thing called a datetime object. But you'll see what that is in just a second. So we have now these 4 different representations of our dates as character strings, and we're going to define a little function here to do our date conversion. And this is probably going to be the most confusing thing we're going to do all day, at least as far as Python programming goes, because it's definitely not, it's not terribly difficult, but it's not something you would be familiar with. But we'll make our function called convert. And what should come into convert is a parameter called date. All convert is going to do is convert a string that represents a date to a datetime object in Python. This datetime object is something that Matplotlib will recognize as a date and will then nicely be able to plot things like several years of data without any kind of weird jumps between the values. What we're going to return from our function, because you remember functions, you always have to have a return value, is datetime dot strp time. I don't actually remember what that stands for. It's something about string parse or something. Yeah, we'll call it string parse time. Doesn't really matter, but this is our function that will convert our dates from strings to a datetime object. We want it to work on whatever value is given to date. So that's the parameter that's passed in. And the format is what comes next. So the format is the format of the character string in terms of how it is represented in the character string. So this will look a little bit weird maybe, but the first thing you can list is %y. The capital Y indicates that the first part of this character string will be 4 characters to represent the year. After this, there's then %lowercase m, which means the 2 characters that follow after that will represent the month. And then %lowercase d is that the 2 characters that then follow will be the day. And then since we have hours, there's a %H and then a %M for the hours and minutes. So that might look a little bit weird. In fact, what I'm going to do here is I'll just, yeah, why not? I will add in some dummy date. And let's say we wanted to represent our dummy date, so today, as a character string. So it's 2018. It's the month of October. It's the 17th. Is that right? Yeah. 17th of October. And right now it is 11:25. So 1:1 for the hour, 2:5 for the minute. So here we have represented our date as a character string. This is the same format that the dates are in the data file we're working with. And as you can see here, the first 4 values are for the year. If you put a capital Y, then what this parsing thing does is it looks for 4 characters at the start that it will convert as a year value. If you put lowercase y, it will only look for 2 characters because sometimes your data only have the first 2 numbers to represent the year. After that, then it's month, day, and so you can kind of see the format here, I guess. Is that right? You kind of understand how the date is represented here, and then what we're going to do is we have to say, well, if we want to convert our date to a date time object, we have to tell it what is the format of the date in the input string that we're going to convert. So I'm going to run the cell up here to define this convert function. I've got dummy date here, and if I do a convert of dummy date and run that, what I get back is this thing that says datetime.datetime 2018 10/17/11/25. In the format of a datetime object, the first thing it lists is the year, then the month, then the day, then the hour, and then the minutes of that hour for that given date. This is all we're doing, is converting it from a string into this sort of special thing that NumPy or that Matplotlib knows how to handle for plotting a continuous range of dates on a horizontal axis. Yeah.
I got an error. Age is a bad directed in format, then process with y and.
So maybe somewhere here in the function definition there's an issue, I would guess. There basically should be a % sign before each one of the letters that we use to define this. So yeah, capital versus lowercase makes a big difference here as well, and it will not be happy if it has, for instance, 2 lowercase m's or something like that. So anyway, this is going to convert our dates into these special date time objects, and we can do that now using a new variable that we'll call winter_dt, which I'm just going to use to indicate this is a date time object. Those of you who were in the NumPy lesson last week had the experience of learning a little bit about list comprehension in Python. It's kind of like a shorthand way to do for loops, and for very simple tasks, it's kind of the easy way to process through your data without actually writing out a for loop. So we're going to have this winter dt where we convert date. So we're going to use our function called convert to convert date for all of the values of date that would be in the list of values winter_str. So this probably looks weird if you've seen things in pandas. Essentially all we're doing is doing a for loop that's like for date in winter string, convert date, and then store that in winter dt. I know that we've been doing Python stuff now for like more than 2 hours, so I don't fully expect that you kind of know the details of what's going on here. But the point is that this is our way in which we can go through each one of the dates in our winter string list of dates, apply our convert function to each one of those dates, and then store that in a variable called winter dt. This is actually going to make a list of values called winter dt because I've put this whole thing in square brackets. This is Python shorthand. It's very convenient, and we could spell it out. In fact, let's put my sort of, I don't know if this is a wise idea, but let's just do it this way. We'll write one of them out the kind of normal full-length way, where we would make a variable called winter dt, and it's going to be an empty list. So we're just going to say winter dt equals a pair of square brackets. that defines a list object in Python, but doesn't put anything in there. Then we can say, what do we want to do? Well, let's do a for loop for date in winter underscore str. So we'll do a for loop over each one of the dates we have in our winter string variable. What are we going to do inside the for loop? Well, what we want to do is to do a winter dt.append. So we're going to add a value to the winter dt list, and the value that we're going to add is going to be convert date. So I don't know whether this is any better to explain it this way, but this is maybe more familiar in terms of what we've done. We're going to make an empty list, loop over all of the values of winter string, and we'll just call our variable date inside the loop. So each time we go through one value, we'll assign that value the name date. And then what we're going to do down here is we're going to convert date into a date time object and append that value to a list called winter underscore dt. So just by a show of hands, how many of you think you have some idea what's going on here? That's not great. So I fully appreciate that this is not necessarily a simple thing. Let's do it one step more spelled out, I guess. And let's call something called date now equals convert of the variable date. So we'll do this in one step first, where we're going to define a variable called date now that is the current date in our list that has been converted to a date time object. Then as a separate step, we'll just append date now. So each time through this loop, we're going to add one date to this list called winter dt, so that in the end, every single one of the dates we had in our list of dates for the winter of 2012 to 2013 will then be stored as a date time object in this new list called winter dt. I don't know if it's easier to understand that way, but if we just try to not have too many steps that happen in one line, sometimes that helps, that you can kind of see line by line what's going on. That little bit of code here, those 4 lines, is exactly the same thing that happens on one line here. There's no difference. In fact, this one line might even be a bit faster. I don't know exactly why that is, but I think it is slightly faster if you do things this way. For our purposes, that doesn't really matter. But these two things are basically the same. So when you see this winter dt line, it's the same as just typing out a for loop to do this. With our for loop, the one other thing we have to do at the end is we want to convert this back to a NumPy array, because what we started out with is a winter dt list, and we now need to do one last step here, which is to say that winter dt equals np.array. That's the function in NumPy that converts any kind of collection into a NumPy array. So it converts a list to a NumPy array, and the thing we want to convert is winter dt. So this just changes our list into a NumPy array. Same thing happens for the other values here. So magical things might happen inside Jupyter that you don't understand at this point, but if all is good, you can run this cell and you hopefully won't get any error messages. And you can trust me that what's happened is we've converted our dates into these date time objects that will now make life better when we go to plot our results. So if we go down to the cell below here, you can see that what we're doing again is we're creating a new subplot with 2 rows, 2 columns, same figure size as before. In fact, everything is the same way that we did it before when we created the subplot. You can just run that cell rather than typing it in again. Nothing special here, it's just an empty plot window. Then we've got some stuff here. This all should look familiar because this is just copied and pasted from the cells above to make our plot for the winter temperatures and to set the y-axis limit. There is one small difference here, and that is that now we do list a variable to plot on the x-axis. So instead of plotting with the index value, we now list winter dt because we want time on the x-axis and temperature on the y-axis. So we list winter dt, spring dt, etc. Otherwise, the format of this plot command is basically the same thing we did before. Now we're going to make our plot look a little bit nicer. And one of the things we can do is to do an ax11.grid. This will turn on grid lines for the top left plot. And then of course, since we want to turn the grid lines on the other plots, we then do the same thing for ax12, 21, and 22. If you're curious, there are ways to do for loops to do the same kind of thing, so you only have to type in once that you're going to turn on the grid command, but I'm trying to not mix in too many loops and other things since I've already exposed you to list comprehension, which is nasty enough. We can give a figure title, and the way that we do that is fig.subtitle, I believe. So it's kind of like the super title, the one that's on the top of the whole thing. And we could call this like seasonal temperatures, Helsinki Malmi Airport. Or you could call it, whatever. It doesn't matter, just to sort of demonstrate how this works. Now, there's a couple other things I've just thrown in here, just mainly for your reference later on. They're not so important to understand in detail at the moment, but these are things about just some extra stuff you might want to do. One of those things is to rotate the x-axis labels a little bit, because when you put in a date for the label on the x-axis, it's often kind of long text. It's not just like one number, which means that usually they overlap each other a little bit. We can get around that by doing this plt.set p, and then this kind of nasty thing here, ax11.x-axis. You can probably just copy and paste the one from below and edit it if you want. Get major tick labels, comma, rotation equals 20. I know I'm typing fast. What this is going to do is just take the x-axis labels and rotate them by 20 degrees. You'll see what this looks like in the plot below, but trust me, it looks much better this way than if you do it without rotation. We're going to then add some axis labels, so to like label the values on the axes, and the first one's going to go on the x-axis, so these are going to be we should do this on the bottom two plots, because if we put the axis labels on the ones in the top, it kind of gets messy. But for the bottom row, we can say that ax12, so that's going to be no, actually, I guess, yeah, it should be ax21. Second row, first column, set x label, and we'll just set it equal to date. And then here, for the line below that, we can do an ax11, so top left, dot set underscore y label. And you can type in something shorter if you want to not type in temperature deg C. It may be easier to copy and paste and edit these things a little bit. We're going to add one last thing here, and that is to label each one of the plots with some text so that we know which one is which month, even though we now have the dates we can still make it easier for the people who look at the plots to right away see that AX11 is winter. So if we do AX11.text, that will put some text on the figure. And when you give the text command, I guess we've already seen it once. You give the, no, have we seen it? Yeah, we did. Yeah, for the temperature in early June. So for this, you give first the x coordinate, and because we have date on the x-axis, we have to give this in the format of a date time object. So that's why you have to have this weird date time thing here. And it's going to be 2013, the month of February, and the 15th of February is where we want to put this text in terms of the horizontal x-axis. And we'll put it at minus 25 degrees for the y position. The text itself will be winter. So probably you're going to have typos when you go to run this. Hopefully that's not the case, but that's it for what we have to type in. And if you hit Shift, Enter, and cross your fingers, hopefully you end up with a plot that looks something like this. So you can see here now we have our winter, spring, summer, and fall all with their own labels. We've got different colors to help indicate the different temperatures for the various seasons. And the cool thing here is that we have horizontal axis labels that are the actual dates of the observations. So if you had many years of data, this works out quite nicely to give you a kind of continuous range of dates without the weird jumps you would have if you interpret the date as a numerical value. And I hope that at least on some level, it's sort of satisfying to think that when you sat down today, more than likely you didn't know the first thing about how to plot any data in Python. And now, already within the one lesson, we've gotten to the point that you can do some plotting of kind of cool things like different seasons on different plots, various colors, and do some basic plot formatting. There's a lot more you can do with NumPy and Pandas and Matplotlib combined to do really interesting plots. In fact, if you think back to the first lesson that we had when we showed that nice little animation of the temperature anomalies with like the different size balls that sort of got different sizes based on how big the temperature anomalies were, I'm fairly sure that that entire thing is done with NumPy and Matplotlib. So once you kind of get a handle on the basic skills, there's a lot more you can do with this combination. Are there any questions at this point? We have maybe one thing we're sort of reluctant to announce, and that is that the exercise is not quite ready to go. So it should be, I think, by the exercise session tomorrow morning, it should be all set. But we're still fixing a few things with the exercise that we've not yet been able to resolve. So exercise 7, the links won't be working yet, but they'll go up soon, and we'll put a post on Slack when that happens. Otherwise, this is our last lesson for the Geo-Python course for those of you who aren't continuing on, and I hope that, that you found the course to be useful and interesting. One of the things we're going to add to the lesson, I think, for this week is a little bit of, well, another short e-form where you can give us some additional feedback about how the course has gone. This is the first time we're doing it with the Jupyter notebooks, and now that you've gone through from start to finish, it would be really useful for us to see how that Jupyter notebook experience has been, and particularly if there are technical problems you've encountered, it would be nice for us to know about those things. So we'll include that in the exercise for this week. Otherwise, for those continuing on to the Intro to Quantitative Geology course, I'll see you all in period 2. And I guess
the same thing for the other GIS. A practical thing, so the lessons in next period for both of our courses, they are on Mondays, so we will have a kind of a slight change in the schedules.
Yeah.
Yes.
It says it's from 12 to 4. Is it for 4 hours or 3 hours?
year it varied a bit, so it might take 4 hours, but typically we try to be a bit faster. Yeah.
But, yeah, if there aren't any questions or any other things, we'll be in touch on Slack about the exercise, and thanks. We hope you enjoyed the course.